Okay, so at time t is 87, right? The machine fails, and because it failed, so we need to do the repairing. And at this particular stage, the state of the system or state of the machine is down. Okay, the repair activity is completed at time t is equal to 190, and the machine status changes to busy. While the machine is down, a customer arrives at time t is equal to 110. A customer arrives at time t is equal to 101, and the associated demand decreases the stock on hand by 1 unit. So K, capital K at time 101 is equal to 1. Right, at time t is equal to 119, the repaired machine resumes processing of the unit whose processing was interrupted at the time of failure. That unit completes processing at time t is equal to 127. So from time t is equal to 127 to time t is equal to 157, no customers arrive at the warehouse, and consequently the inventory reaches its target level or base stock level. So capital R is equal to 5, right? At that time t is equal to 157, the at which the machine will stop producing any more further units. So the simulation run finally terminates at time t is equal to 165. um, Next step would be to like determine the probability distribution of machine status. So consider the machine status over the time interval 0 to capital T, right? And capital T here is 165. So let Ti be the total idle time over the whole interval, Tb, which is the total busy time over the whole interval, and Td, the total downtime or the whole time interval. So here the probability distribution of machine status is then estimated by the ratios of time spent in a state to total simulation time. So in order to calculate the idle time, let's go back to that figure. So let's have a look at this schematic diagram, right? Idle is 0 to 35, so that is my 35 minutes, and there's also a small portion of idle time, so that's going to be 165 minus 157 plus 35 divided by this whole 165. So that is basically my idle time, and the value comes out to be 0.261. Second one is machine busy, so that would be the time machine was busy divided by the total time. So here in order to calculate the machine busy time, that would be here from 87 minus 35, that's one portion, plus there is another portion also, 157 minus 119, and then what you need to do, divide it by 165, and the value comes out to be 0.545. Okay, third one is machine downtime. So that's basically 119 minus 87 and divided by 165. That's giving you a result of 0.194. And when you add all those probabilities, so the sum should be unity. So if you add 0.261 plus 0.545 plus 0.194, so it should be 1. Now let's talk about machine throughput. Uh, so machine throughput, here let's consider the number of jobs completed, and we are representing this by CT, right, for the whole interval. And if we can see from the diagram, 9 units were being completed. So the throughput is a measure of effective processing rate, and you can say that the expected number of jobs completed divided by total time. So let's go to the diagram. um, so here you can see each step up is showing job completion. So here 1, right, 2, 3, 4, 5, 6, 7, 8 and 9. So 9 divided by my total time, which is 165. So the answer is 0.0545. um, let's talk about customer service level. So consider customers arriving at the warehouse with a demand for products. Let NS be the number of customers whose demand is fully satisfied over the interval. So our interval was from 0 to 165, and NT is the total number of customers that arrived over the whole time interval, right? So the customer service level is basically the probability of fully satisfying the demand of an arrival at the warehouse, and this is basically NS divided by NT. If we can see, there were 3 customers arrival and 2 customers, their demands were fulfilled, and one customer was one customer's demand was unmet. So let's go to that figure. Okay, so here you can see that this thing is dropping, right? Our inventory is dropping at t is equal to 35. This means that we had a customer, so, and the demand was satisfied. Let's go here, the second customer, and that customer is arriving at t is equal to 69, and here the demand was not met. Okay, so that's customer number 2, and here is another drop here. So at time is 101, we have another customer, and you see the demand was satisfied because we are not going to negative inventory. So we had 3 customers, 2 were satisfied. So here we can say that, okay, 2 divided by 3, the answer is 0.6667. So in discrete event simulation example, we are also interested in finding the probability distribution of finished products in the warehouse, right? So consider the probability that the long-term number of finished units in the warehouse is being denoted by capital K, right, is at some given level small k. These probability are estimated by the expression here. So k, this small k could be 0, 1, 2, or 3, or 4, or 5. It cannot be greater than 5 because our capital R was 5. We don't want to produce, like, we don't want to keep more than 5 units in our warehouse, right? So probability that small k units in stock is equal to total time spent with k units in stock divided by total time. So here, let's say small k is equal to 0. So the time was 75 here, minus 69 divided by 165. So the probability is 0.036. Just for the sake of understanding, I'm just taking k is equal to 2. What is the probability that we had k units in stock, right? So that would be total time spent with 2 units in stock divided by total time. So here this small r is 2. So how much time is this? 55 minus 45, and then I'm gonna go to the second portion here also. um, that's 100 minus 85, and the third one here, this one, is 137 minus 127. So it's going to be 10 plus 15 plus 10, that's 35, divided by 35 divided by 165, right? So the answer is 0.21. Regarding different discrete event simulation modeling languages and tools, so we have plenty. Basically, a simulation model must be ultimately um, transcribed into computer code using some programming language. A general purpose program could be C++ or Visual Basic. I like VBA coding of Excel very much, and it's very easy to do simulation, Monte Carlo simulation sampling. In addition, if someone wants to buy um, paid languages, so Arena is also available, and I think student version is also available for like with limited features. And in addition to that, you can also do simulation in MATLAB. Other than that, we have Pro Model, um, and we have GPSS, SLAM, um, and ComNet also. However, you will be like buying the license version in order to get full features. So that's it for lecture 3, and we are done with it. In our next class you'll be talking about statistics and probability, and um, then we will be talking about how to use probability distributions, and how to sample from probability distributions which serve as an input to simulation. Okay, thank you.